This is our only window. We must hit the flagship here.
Are you sure the approach is clear?
The sonar report confirms it. We engage immediately. Look here, this angle is wrong.
It can't be. I double-checked it.
We have to try something else. This isn't working. Target bearing 270. All ahead slow.
Aye, Captain. Course steady.
Bearing 270, range 10,000. Standby tubes 1 and 2.
January 1941. The early morning fog clung to the piers of the Brooklyn Navy Yard. Cold Atlantic winds whipped across the decks of anchored destroyers, carrying the briny scent of the harbor. Sailors, bundled in heavy coats, moved silently along the gangways, their boots clanging against steel. In the shadowed hold of one vessel, torpedoes lay stacked in neat rows, sleek, deadly, and yet unreliable. Each was a promise unfulfilled. Tests had failed, guidance systems faltered, and engines sputtered. Officers scowled over blueprints, rubbing weary eyes, the tension palpable. The Navy knew the world was at war. Across the oceans, Germany and Japan were pressing forward with relentless efficiency. The United States, still officially neutral, was unprepared for the scale of modern naval warfare. In nearby workshops, engineers at General Electric hunched over electric motors, wiring intricate circuits by hand. Sweat mixed with the scent of oil and varnish as they worked feverishly against the clock. Every design choice, every connection, could determine whether American submarines would strike effectively or drift silently into failure. This was more than engineering. It was survival, and the race to create a reliable torpedo had only just begun. The problem was clear. America had no torpedoes ready for the war it would soon enter. By early 1941, the world was already engulfed in conflict. Across Europe, the German Wehrmacht had conquered Poland, Norway, Denmark, France, and the Low Countries. Britain, isolated yet unbowed, stood defiant against relentless Luftwaffe bombing campaigns. In the Pacific, Japan had begun its expansionist push into China and Southeast Asia, testing the limits of American patience and industrial capacity. The United States, still officially neutral, was caught in a delicate balance, supplying allies through the Lend-Lease Act while preparing for a potential global confrontation. Within this tense atmosphere, the U.S. Navy faced a glaring weakness. Its submarine fleet, crucial for patrolling the Atlantic and protecting supply lines, lacked reliable torpedoes. The standard Mark 14 torpedo, developed in the 1930s, had been plagued by design flaws. Depth mechanisms were inaccurate. Magnetic detonators often triggered prematurely or failed entirely. Straight-running torpedoes missed targets by hundreds of yards. Repeated tests at the Pacific Fleet's submarine base in Pearl Harbor revealed a humiliating truth. The Navy's primary undersea weapon was failing before it ever left the launch tube. Sailors trained in torpedo drills grew frustrated. Captains recounted night after night of missed opportunities during exercises, torpedoes striking harmlessly into sandbars or passing beneath practice targets. Engineers in the Bureau of Ordnance were caught between a relentless testing schedule and the slow pace of bureaucratic approval. Reports of malfunctioning torpedoes piled on desks, some marked top secret, others ignored in the rush to expand the fleet. Confidence among crews faltered. If war came tomorrow, they knew their torpedoes might betray them. The Navy's unpreparedness was more than technical. It was strategic. Germany's U-boats prowled the Atlantic, sinking convoys with ruthless efficiency. Japanese submarines in the Pacific were already equipped with functioning torpedoes, giving them a deadly edge. American war planners recognized that without a reliable undersea weapon, the U.S. fleet could be crippled before it fully engaged. The problem was urgent, and failure was not an option. Meanwhile, America's industrial capacity remained its secret advantage, but one that had yet to be fully mobilized. General Electric, Westinghouse, and other engineering firms had the expertise, but had not been tasked with wartime submarine armaments at scale. Converting civilian engineering knowledge into combat-ready technology was a formidable challenge. Factories were retooled, engineers drafted into special Navy committees, and prototype workshops sprang up in secrecy. Every day lost in development meant another day the Navy entered the war underarmed and vulnerable. By January 1941, the crisis had become impossible to ignore. The Navy's leadership convened urgent meetings in Washington. Maps and charts of the Atlantic and Pacific theaters lined conference rooms. Reports of torpedo failures were read aloud. The stakes were clear. America could not wait for perfection. It needed reliability, speed, and innovation. And in the shadows of these high-stakes discussions, the fate of countless submariners rested in the hands of a handful of engineers, tasked with making the impossible work. This backdrop of global tension, technical failure, and industrial urgency set the stage for one of the most critical engineering feats of the war: designing electric motors capable of powering torpedoes that would finally meet the Navy's exacting standards. The clock was ticking, and every moment brought the United States closer to a confrontation for which it was dangerously unprepared. While the Navy struggled with torpedo failures, American industry was quietly gearing up to meet the challenge. General Electric, already a giant in electrical engineering, was called upon to tackle a problem that bridged science, mechanics, and human survival. Torpedoes required propulsion systems that could operate silently, reliably, and under extreme underwater pressures. For the engineers at GE, this was uncharted territory. Electric motors of the size and durability needed for submarine torpedoes had never been mass-produced before. Designing such motors involved meticulous calculations. Engineers had to balance power output with battery efficiency, ensuring that a torpedo could travel hundreds of yards at precise speed without overheating. The motors had to function in salt water, resist shock from launch, and maintain exact rotational speed to ensure accuracy. Every component was subjected to testing protocols that were rigorous, yet time-consuming, because failures at sea would mean lives lost. In early 1941, prototypes were fragile. Wires burned out, bearings seized, and even slight misalignments could throw off performance. Coordination between the Navy and GE was intensive. Technical committees were formed, composed of naval officers and civilian engineers. Daily meetings reviewed test data, troubleshooting failures, and refining designs. In laboratories filled with the smell of oil, varnish, and solder, engineers worked in shifts, often through the night, rewiring and rebalancing motors for the next round of testing. GE's industrial plant in Schenectady, New York, became a hive of activity, producing components in small quantities to refine tolerances before full-scale production could begin. But technology was only one part of the equation. The Navy's operational requirements were unforgiving. Submarines required torpedoes that could be launched from various depths and angles, navigating underwater currents with precision. Each test had to simulate real combat conditions. Initial runs revealed persistent problems. Torpedoes veered off course, batteries drained too quickly, and motors produced noise that could betray a submarine's position. Engineers faced the dual pressure of technical difficulty and the moral weight of human lives, depending on their success. Early prototypes, though imperfect, represented a critical step forward. Electric propulsion promised a solution to the Mark XIV's chronic failures. Unlike the steam-driven predecessors, electric torpedoes could operate quietly, reducing the chance of detection. Yet scaling up from one working prototype to hundreds of combat-ready torpedoes was an entirely different challenge. Factories had to adapt precision machining techniques to wartime production speeds, while maintaining the tolerances that determine success. Supply chains for copper, insulation, and batteries became as vital as the engineering itself. By mid-1941, the first GE-built electric motors were ready for field testing. Submarine crews were skeptical. Previous failures had eroded trust, but the Navy recognized that these tests could determine whether the U.S. could match or surpass enemy undersea capabilities. Each launch was carefully documented, every deviation analyzed. Slowly, patterns emerged, and design tweaks improved reliability. This period of relentless trial, adjustment, and collaboration underscored a critical reality of wartime innovation. Victory depended not just on manpower or strategy, but on the quiet, persistent work of engineers converting theory into tools of war. The Navy's torpedo crisis highlighted the interdependence of human skill, industrial capacity, and technological ingenuity, a theme that would define the coming years of submarine operations. From these early experiments, the stage was set to explore the story from multiple perspectives. The human toll, the technological breakthroughs, the tactical challenges, and the leadership decisions that intertwined in the race to produce America's first reliable electric torpedoes. Each angle would reveal a different facet of the struggle and the eventual triumph, preparing for the intense climax of the narrative. For the men who relied on these torpedoes, failure was personal. Submarine crews trained for months, memorizing drills, calculating firing solutions, and rehearsing under simulated combat conditions, only to see torpedoes miss targets by yards or fail to detonate entirely. The frustration was tangible. Sailors confided in one another during long patrols, their conversations a mix of anxiety and gallows humor. "We can get to the target," one submariner noted in a diary entry, "but what good is a torpedo that won't run straight?" Each malfunction was not just a technical flaw. It was a potential death sentence. The psychological weight of unreliability compounded the pressure on every captain, every gunner, every deck officer, shaping an invisible tension that followed the fleet across oceans. Even on shore, the human element was relentless. Engineers worked 12-hour shifts, soldering circuits, adjusting bearings, and meticulously documenting every failed attempt. Many were young men with families, aware that the success or failure of their work could cost lives. Letters home often mentioned the long hours and sleepless nights, but rarely the exact nature of the task. Secrecy enveloped the work like a shadow. They were ordinary men performing extraordinary labor, bridging the gap between industry and warfare with quiet heroism. The challenge faced by General Electric was unprecedented. Electric torpedoes required motors that could operate flawlessly underwater, silently, and at consistent speed. Engineers had to calculate tolerances to fractions of a millimeter. Even minor misalignments could alter propulsion, send a torpedo off course, or generate noise detectable by enemy hydrophones. Battery technology, still in its infancy, presented another hurdle. Sufficient power for extended range had to coexist with compact size, seawater resistance, and safety. Prototypes often failed spectacularly. Bearings overheated, insulation melted, and motors occasionally froze entirely. Each setback demanded analysis, redesign, and repeated testing. Innovations emerged slowly. New alloys for shafts, improved insulation materials, and precision machining techniques allowed motors to run longer without overheating. Electric propulsion, unlike steam-powered predecessors, offered the promise of silent running, a tactical advantage that would become decisive in the Pacific War. These technological breakthroughs were the quiet victories that occurred far from the battlefield, but were no less vital. Leadership played a crucial role in navigating the torpedo crisis. Navy officers were forced to balance operational readiness with the risk of failure. High-ranking officials in Washington demanded rapid results, while fleet commanders pushed for rigorous testing to avoid catastrophic errors at sea. Decision-making was complicated by bureaucratic inertia, secrecy, and a novelty of the technology. Rear admirals and bureau chiefs frequently visited laboratories and shipyards, scrutinizing test results, questioning engineers, and urging speed without compromising safety. They understood that innovation under pressure was a double-edged sword. Premature deployment could cost lives, but delay could leave the Navy vulnerable to enemy submarines and surface ships. Their task was as much psychological as technical, maintaining morale among crews, reassuring policymakers, and ensuring industrial partners delivered on an unprecedented scale. Leadership was measured not just in orders given, but in fostering trust, patience, and persistence under extreme pressure. This section of Angles reveals how deeply intertwined human endurance, technological innovation, and leadership judgment were in solving a problem that at first seemed insurmountable. Crews endured uncertainty, engineers wrestled with impossible specifications, and leaders orchestrated a fragile balance of urgency and caution. Together, these elements converged toward the moment when the first successful electric torpedo would finally leave the water with precision and reliability, setting the stage for the next section of Angles, where tactical and enemy perspectives would further illuminate the stakes of innovation. The failure of torpedoes had immediate and dangerous tactical implications. Submarines, intended as stealthy hunters in both the Atlantic and Pacific, were handicapped by their primary weapon. Exercises revealed the stark reality. Targets that should have been sunk remained afloat, convoy patrols were ineffective, and strategic maneuvers were compromised. Commanders were forced to develop contingency plans, relying on surface gunfire or avoidance rather than decisive strikes. The advent of reliable electric torpedoes promised to reshape naval tactics. Silent running allowed submarines to approach targets undetected, striking with precision and disappearing before counterattacks could materialize. Patrol patterns could be extended, and coordinated attacks became feasible. Commanders began envisioning scenarios where a single submarine could disrupt supply lines, cripple warships, and alter the flow of battle. The tactical transformation hinged entirely on the reliability of the torpedo, a weapon that until now had betrayed those who depended on it. Comparing American deficiencies to enemy capabilities only heightened the urgency. Japanese Type 93 Long Lance torpedoes, for instance, demonstrated superior range, speed, and reliability. German U-boats relied on torpedoes that had undergone iterative improvements through combat experience. Allied intelligence reports emphasized the gap. U.S. submarines were, in some cases, technologically outmatched, their crews hampered by tools that could not perform as expected. Understanding the enemy's edge galvanized both Navy leadership and industrial partners. Engineers were not designing in isolation. Every modification, every test, was measured against the standards already established by adversaries. The stakes were clear. Failure would mean American submarines entering combat with inferior firepower, at the mercy of more experienced and better-equipped foes. The urgency of catching up was not hypothetical. It was existential. Beneath the technical and tactical dimensions lay a moral imperative. Each torpedo represented more than engineering complexity. It represented human lives. Submarine crews trusted their weapons implicitly, and every malfunction carried a potential cost measured in death or mission failure. Engineers and factory workers carried a quiet burden. They were shaping the outcomes of battles from assembly lines and workshops, far from the chaos of combat, but with consequences equally grave. Industrial capacity became a moral instrument of war. Factories were retooled, supply chains tightened, and workers were often pushed to extremes. Every successful prototype, every incremental improvement, reinforced the understanding that innovation could save lives. Conversely, delays or failures were not abstract. They threatened the very men who would carry these torpedoes into action. The war effort depended on precision, perseverance, and an understanding that engineering was inseparable from humanity. By examining these angles together, the human, technological, leadership, tactical, enemy, and moral industrial perspectives, the full complexity of the torpedo crisis comes into focus. It was not merely a matter of designing a better weapon. It was a multidimensional struggle that connected sailors in the Atlantic and Pacific with engineers in New York factories and policymakers in Washington. Every decision, every failed test, every sleepless night brought the Navy closer to a solution, or further from survival. This layered understanding sets the stage for the climax/turning point. The moment when the combined efforts of human ingenuity, industrial capability, and tactical necessity produced a torpedo that finally worked reliably. The stage is set for suspense, technical triumph, and operational impact, a convergence that would redefine submarine warfare for the United States. Spring 1941. At a secret testing range along the New England coast, the tension was tangible. The morning air was crisp, carrying the metallic scent of machinery and salt water. Submarine crews, Navy officers, and a small contingent of General Electric engineers gathered on the deck of a test platform, their eyes fixed on the narrow channel where the first operational electric torpedoes would be launched. Every man present understood the stakes. Failure here would echo across the Atlantic and Pacific, undermining confidence and costing lives in the inevitable war to come. The first torpedo slid into the water with a hiss of compressed air, its hull gleaming under the rising sun. Silence fell as the crew tracked its course. Seconds stretched into eternity. The torpedo veered slightly at first, then corrected itself. It ran straight, smooth, silent. The electric motor, the product of months of design and sleepless nights, performed flawlessly. On shore, engineers exhaled, some shaking hands, others too stunned to speak. Captain James Doyle of the testing submarine noted in his log, for the first time, the weapon behaved as it was designed. Reliable, silent, deadly. Subsequent launches followed, each one an incremental confirmation of success. Adjustments were minor, battery placement fine-tuned, bearings lubricated, propeller alignment corrected, but the underlying breakthrough was unmistakable. Unlike the Mark 14 torpedo, which had earned the nickname the Dud, the new electric torpedo exhibited consistency under pressure. Its silent motor allowed submarines to approach targets undetected, addressing the tactical vulnerabilities that had plagued exercises for years. The reactions of the men present captured a spectrum of relief and exhilaration. Sailors who had previously doubted their tools now felt a renewed sense of purpose. Engineers, many still in their white lab coats, quietly acknowledged that their months of labor had directly contributed to national defense. Navy officers allowed themselves rare smiles, realizing that for the first time, U.S. submarines could operate with confidence. Reports were immediately drafted for higher command. The electric torpedo was not just a prototype. It was ready for operational integration. The testing was meticulous. Targets simulated enemy vessels at various ranges and depths. Each launch was documented in excruciating detail. Speed, trajectory, depth control, and detonation were monitored and recorded. Failures, when they occurred, were minor and instructive rather than catastrophic. This iterative process confirmed that the electric motor design could be reproduced reliably, paving the way for mass production. By late spring, the Navy had gained a weapon that met, and in some respects exceeded, the capabilities of comparable Japanese and German torpedoes. This breakthrough represented more than technological success. It marked a turning point in the confidence of the U.S. Navy. For years, submariners had been forced to question their primary weapon. Now, with a reliable electric torpedo, operational planning could proceed without the shadow of uncertainty. Patrols could be extended into hostile waters with greater risk tolerance, and commanders could envision coordinated attacks on enemy shipping that had previously been considered impractical. The culmination of this effort was a testament to the convergence of multiple forces: human perseverance, industrial expertise, and naval leadership. Engineers who had worked through countless prototypes, sailors who had endured repeated failures, and officers who had navigated the bureaucratic and tactical complexities now witnessed the first tangible reward of their combined efforts. The silence of the electric motor in the water was more than a technical detail. It was a symbol of American ingenuity applied under the relentless pressure of war. The success at the New England testing range set the stage for deployment in active combat. Electric torpedoes would soon be loaded aboard submarines bound for the Pacific Theater, ready to confront Japanese shipping and warships. Crews trained in long, grueling drills would finally have a weapon they could trust, and the Navy could shift tactics from cautious engagement to confident offensive operations. The moment of triumph was not theatrical. There were no parades, no grand announcements. Only the quiet satisfaction of engineers and sailors who understood that the invisible work done in factories and workshops had produced a weapon that could change the course of naval warfare. Yet this victory, though significant, was only the beginning. Operational challenges lay ahead, and the electric torpedo's true test would come in the open ocean, under fire, against a skilled and determined enemy. By mid-1942, the first electric torpedoes were being deployed aboard U.S. submarines in the Pacific. Silent, reliable, and deadly, the Mark 18 torpedo, the first American torpedo powered by General Electric's electric motor, represented a radical improvement over its flawed predecessors. Submarine crews, once skeptical, now felt a renewed confidence as they prowled the waters off Japanese-held islands. Every launch was calculated with precision, and the predictable behavior of the torpedo allowed captains to plan attacks with unprecedented accuracy. The first combat successes were both dramatic and instructive. Off the coast of the Solomon Islands, USS Wahoo, under the command of Lieutenant Commander Dudley Mush Morton, executed a daring patrol against Japanese shipping lanes. Using newly issued electric torpedoes, Morton's crew struck multiple enemy vessels in rapid succession. The torpedoes ran silently through the water, unseen until impact, and detonated with devastating effect. Reports from the patrol emphasized the contrast with previous operations. Fewer misses, no erratic behavior, and no premature detonations. Submarine officers praised the weapon in after-action logs, noting that its reliability fundamentally altered the way they approached attacks. These operational successes had immediate strategic implications. Japanese supply lines, once considered secure against American submarines, were now vulnerable. Convoys that had previously escaped due to torpedo failure were intercepted and sunk. Commanders could coordinate attacks over multiple submarines, confident that each would deliver a precise strike. The silent electric motors allowed submarines to approach convoys undetected, reducing the risk of counterattack and increasing the effectiveness of patrols. The impact extended beyond a single theater. Reports sent back to Washington highlighted the transformative effect of the electric torpedo on fleet morale and strategic planning. Admirals began revising operational doctrines, incorporating the new torpedo into offensive strategies that emphasized stealth, precision, and sustained pressure on enemy logistics. In essence, the torpedo had shifted the balance from cautious experimentation to confident, proactive engagement. Engineers at General Electric followed these developments closely. Each operational report validated months of painstaking work in laboratories and workshops. Small teams monitored performance, noting any irregularities, and applied rapid improvements where necessary. Factories ramped up production, ensuring that each submarine could be fully stocked with electric torpedoes. The industrial and technical collaboration that had seemed theoretical during early testing was now proving itself in the crucible of war. The human dimension remained central. Submarine crews, who had endured years of uncertainty with defective weapons, now approached missions with a renewed sense of purpose. Diaries, letters, and after-action reports reveal the psychological relief of operating with a reliable torpedo. The stress of unpredictability lifted, allowing crews to focus on strategy, navigation, and teamwork. Morale improved, and a culture of trust developed between sailors and the engineers whose work made survival possible. Yet even amidst these victories, challenges persisted. The operational environment of the Pacific was unforgiving. Rough seas, extreme depths, and enemy countermeasures continually tested the torpedo's design. Crews needed ongoing training, and engineers continued refining components to address minor inconsistencies. Each patrol offered both proof of concept and lessons for further innovation. By late 1942, the electric torpedo had fully proven itself in combat. Submarine effectiveness increased dramatically. Japanese shipping losses mounted, and the tactical confidence of American crews reached levels previously unattainable. The successful integration of the electric torpedo was not merely a technological milestone. It was a turning point in the broader campaign of the Pacific War, demonstrating how industrial ingenuity, scientific precision, and human perseverance could converge to produce a decisive advantage. The climax of this story, the first operational victories using electric torpedoes, naturally flows into the aftermath, where we will examine the broader consequences, the scale of American submarine success, enemy losses, industrial implications, and the lessons that would shape future naval strategy. By 1943, the results of the electric torpedo's deployment were unmistakable. American submarines, once hampered by unreliable weapons, were now inflicting significant damage on Japanese shipping lanes. The Mark 18 torpedo, powered by General Electric's electric motor, had transformed the operational capabilities of the U.S. Navy. Submarine captains reported unprecedented success rates, and the once-embattled crews could finally rely on their primary weapon with confidence. Operational records from the Pacific reveal the scale of the impact. Convoys that had previously evaded attacks were intercepted with deadly precision. Ships carrying troops, fuel, and supplies were sunk at a growing rate, severely disrupting Japanese logistics. For the first time, American submarines could conduct coordinated, multi-target attacks without fear of torpedo malfunction. The combination of silent propulsion and reliable detonation allowed submarines to approach closely, execute strikes, and withdraw undetected. A stark contrast to pre-1942 operations where misfires and erratic torpedoes limited tactical options. Industrial reports from General Electric and other manufacturing partners highlight the extraordinary effort behind these operational successes. Factories had scaled production from a handful of prototype torpedoes to hundreds per month. Engineers and assembly line workers, often laboring under strict secrecy, ensured that each component met exacting standards. Innovations in machining, battery design, and insulation had matured to the point where torpedoes could be mass-produced without compromising reliability. These achievements underscore a critical truth. Wartime success depended not only on strategy or courage, but on the silent precision of industrial labor and engineering expertise. The human dimension of these accomplishments was equally profound. Submarine crews, once burdened by anxiety over faulty weapons, now operated with renewed morale. Letters and diaries from the period describe a sense of professional pride and cautious optimism. Officers could plan complex maneuvers with confidence, knowing that their torpedoes would behave predictably. Crews felt a tangible connection to the engineers whose work, far from the combat zone, had directly influenced survival and effectiveness at sea. At the command level, these developments reshaped strategic planning. Admirals revised offensive doctrines, relying on submarines to disrupt enemy supply chains with greater intensity. Electric torpedoes enabled prolonged patrols, aggressive positioning, and the execution of coordinated attacks across vast stretches of ocean. In effect, the operational success of the torpedo created a multiplier effect. Each reliable strike amplified strategic pressure on Japan, hastening logistical strain and contributing to broader campaign objectives. The consequences were not purely tactical. Intelligence reports indicated that Japanese forces recognized the growing threat of American submarines. Convoy strategies were adjusted, escorts increased, and anti-submarine measures intensified. Yet, even with these countermeasures, the silent, dependable Mark 18 torpedo allowed U.S. submarines to maintain a significant operational advantage. Success in combat validated the months of industrial labor, iterative testing, and engineering innovation that had gone into the torpedo's development. The combination of technical reliability, industrial scale, and human trust marked a turning point. The U.S. Navy could now enter engagements with a weapon that performed as intended, giving commanders flexibility, boosting morale, and directly affecting the course of the war in the Pacific. Submarine operations, once limited by uncertainty, became a decisive instrument of strategy, thanks in large part to the quiet work of General Electric engineers and the relentless persistence of submarine crews. By late 1943, the strategic consequences of reliable electric torpedoes were unmistakable. Japanese shipping losses had mounted dramatically. Reports from the Pacific Fleet noted that American submarines, once constrained by defective Mark 14 torpedoes, now sank vessels at rates previously thought impossible. Fuel, ammunition, and troop shipments dwindled under the persistent threat of precise underwater attacks. Logistic lines that had been secure became vulnerable, forcing Japan to divert resources to convoy protection, naval escorts, and anti-submarine patrols. Resources that could have been deployed elsewhere. The numbers tell a stark story. In the first 6 months of operational electric torpedo deployment, the U.S. Navy recorded dozens of successful engagements, each strike reducing enemy transport capacity. Submarine effectiveness metrics rose sharply. Missions completed, targets destroyed, and patrols executed without torpedo malfunction increased dramatically. These quantitative results underscored the tactical and strategic shift enabled by General Electric's innovation. Reliable torpedoes were no longer an experiment. They were a decisive tool reshaping the dynamics of naval warfare in the Pacific. Industrial and technological lessons were equally profound. The successful design, testing, and mass production of electric torpedoes demonstrated the U.S. capacity to transform complex engineering challenges into operational realities. Factories adapted quickly to wartime demands, producing precision components at scale. Engineers developed innovative solutions in materials, machining, and propulsion that would influence not only torpedo design, but broader naval technology in the years to come. The collaboration between government, military, and industry became a model for wartime innovation, emphasizing speed, accuracy, and reliability under pressure. Human stories remain central to these outcomes. Submarine crews grew confident, mission-focused, and increasingly aggressive in operational planning. Letters from officers highlight an unusual blend of technical fascination and professional pride. They were witnessing, firsthand, the results of engineering excellence. Meanwhile, engineers and factory workers, often far from combat, recognized their critical role in sustaining the war effort. Every torpedo produced was not merely a technical achievement, but a lifeline for sailors, a tangible contribution to victory. Beyond the immediate tactical and industrial effects, the electric torpedo shaped long-term naval doctrine. Silent, reliable underwater weapons allowed the U.S. Navy to embrace offensive submarine strategies that emphasize disruption over confrontation. Training programs evolved, emphasizing torpedo handling, battery management, and coordinated fleet tactics. Lessons learned during these early deployments informed future designs, including faster, longer-range torpedoes with improved guidance systems. The experience underscored a fundamental truth of modern naval warfare. Technology and industry, when aligned with human skill, could decisively shift the balance of power. The broader geopolitical impact was also significant. Japanese planners, recognizing the vulnerability of their supply lines, altered operational priorities, often at great cost. The ability of a relatively small number of American submarines to sink critical cargo forced the enemy into a defensive posture. In essence, the innovation of the electric torpedo magnified the effect of limited naval assets, demonstrating the power of precision engineering over sheer numbers. By the end of 1943, the torpedo crisis of 1941, once a source of national anxiety, had become a story of triumph. The combination of industrial ingenuity, technical expertise, and human perseverance had transformed a vulnerability into a decisive advantage. Submarine warfare had been revolutionized, the Pacific theater reshaped, and American naval strategy elevated to a level that would carry the fleet through some of the most challenging campaigns of the war. The story of America's torpedo crisis in 1941 is not simply one of machines and steel. It is a story of human ingenuity meeting urgent necessity. In the shadow of global conflict, when submarines prowled uncertain waters and sailors depended on tools that had repeatedly failed, a quiet revolution was taking place in factories, workshops, and laboratories. General Electric engineers, guided by precision, perseverance, and purpose, transformed a desperate problem into a decisive advantage. The electric torpedo became more than a weapon. It became a symbol of collaboration between human intellect and industrial might. Every turn of a motor, every careful soldering of a wire, every adjustment in a prototype reflected the stakes of life and death at sea. Submarine crews could finally trust the instruments of their survival, while engineers witnessed the tangible impact of their labor. This convergence of human effort, technological innovation, and strategic necessity illustrates a timeless principle. War is won not only by courage and tactics, but by the unseen work that makes victory possible. Beyond the immediate tactical successes, the crisis and its resolution reshaped naval warfare. Silent, reliable torpedoes redefined submarine strategy, allowing the U.S. Navy to strike decisively against supply lines and enemy warships. The lessons learned about industrial coordination, precision engineering, and iterative problem-solving under pressure echoed far beyond 1941, influencing future weapons design and the broader philosophy of military innovation. Perhaps most poignantly, the story reminds us that innovation often arises under constraint. What begins as failure, frustration, or doubt can, through persistence and ingenuity, become a force that changes the course of events. The electric torpedo was not just a tool of war. It was a testament to human resilience, technical brilliance, and the quiet courage of those who worked far from the battlefield. In the end, the crisis of 1941 became a defining moment, a turning point where necessity drove invention, and invention secured survival. The echo of those spinning motors beneath the waves serves as a lasting reminder that even in the darkest hours, ingenuity and perseverance can illuminate a path to triumph.